In general, multi-component reactions are defined as reactions in which 3 or more substrates combine together to form a product. Using this strategy has considerable advantage over traditional step-by-step synthesis. In multi-component reactions, a target molecule is assembled in one chemical step in one pot by mixing starting materials without changing the reaction condition. In this approach, several substrates are put together to build a molecule that contains most of the atoms of starting materials. So enable us to transform readily available substrates into complex scaffold, which is one of the essential goals of modern organic synthesis. The effectiveness of this strategy is not only reflected in the large number of applications, but also pharmaceutical industries use that to produce valuable compounds with remarkable biological activities. Using Mannich reaction is an important strategy to form carbon-carbon and carbon-nitrogen bonds to achieve a beta-amino carbonyl compound. In these 3 component reactions, an aldehyde, ammonia or an amine, and an analyzable ketone contribute to produce alkaloid building blocks, which are essential for synthesizing of biologically active molecules. Using components with different substituents results in creation of 2 chiral centers. Organic synthesis is the art of controlling and put reactants together such a way that do what we want. Within this context, producing an anti-homeric pure molecules is an essential challenge. In this regard, Benjamin Lees, who won Nobel Prize in 2021, represented the first version of asymmetric organic catalyst 3-component Mannich reaction. Indeed, by reaction among acetone, para-and-azidine, aldehyde with different substituents, and make use of S-proline as the organic catalyst, Lees group successfully produced this target with impressive and anti-homeric excess. Now let's go over reaction mechanism. First off, an anti-homeric pure S-proline reacts with ketone to produce an amine. In parallel, the amine, which is protected by PMP, reacts with aldehyde to produce imine. Next, an amine attacks to the imine bond to produce this structure with high accuracy of installing substituents in a specific orientation. Contribution of S-proline plays a crucial role to inducing chirality. In a non-chiral environment, imine bond is equally attacked from above and below the plane, which leads to produce a mixture of products. This reaction passes through a Ch-like transition state in which hydrogen bonds between 2 nitrogens and oxygen are responsible for stereoselectivity of the reaction. In other words, hydrogen bonds lock the amine bond such a way that only one phase is attacked by an amine. After hydrolyzing, desired product is obtained with high enantioselectivity. S-proline leaves the molecule and starts another catalytic cycle. Ugi reaction is a 4-component reaction involving a primary amine, a carbonyl compound, isocyanide, and a carboxylic acid to a 4-alpha-acylaminoamide. In the classical Ugi reaction, amine attacks to the carbonyl group to produce imine. Next, carboxylic acid protonates nitrogen to increase the nucleophilicity of the imine bond. After that, addition of isocyanide to the imine gives a nitrilium ion, which is attacked by carboxylatin ion. Finally, reaction ends up with intramolecular transform of the acyl moiety from the oxygen to the nitrogen atom, which is known as MOM rearrangement, yields the Ugi product. Now let's take a look at this amazing architecture. Spiroheterocyclic structures are a common scaffold of many bioactive natural products. This target consists of benzopyrene and pyrrolidine skeletons, which their 3-dimensional arrangement is crucial to interaction with biological receptors. In addition, such a high functionalized structure converted to a hard target for synthetic chemists. In 2009, Marcaccini group represented a beautiful synthesis route based on 4-component Ugi reaction, which unlike the classical version involved 5 components to produce this complex target with high stereoselectivity. First off, the authors carried out a reaction between 6-methyl-3-formyl-chromone, aniline, cyclohexyl isocyanide, and phenylglycosidic acid in methanol as a solvent. Stirring the mixture at room temperature gave the expected Ugi 4-component product. The mechanism is exactly the same as described before. This molecule consists of a chromone skeleton, which has electron deficiency in 2 positions. So the addition of nucleophiles to this position generates a negative charge on 3 positions, which can be trapped with electrophiles. Using appropriate starting materials has such a crucial importance in modern organic synthesis with the aim of building purposeful molecules. In this example, starting materials are chosen such that the product contains a carbonyl group, which acts as a nucleophile to trap an ionic intermediate generated by the addition of nucleophiles. Marcaccini group used benzylamine as a nucleophile to obtain spiropyrrolidinochromone skeleton. This reaction is highly diastereoselective. To rationalize, let's take a look at this 3D model of the structure. Two non-covalent forces are responsible for the stability of this conformation. Two phenyl rings in its geometry have a stabilizing effect due to pi stacking interaction. This force also plays an important role in the stabilizing of DNA structure. The second stabilizing effect comes from this hydrogen bond between oxygen of carbonyl group and hydrogen attached to the nitrogen. So the molecule is locked in this conformation. When benzylamine approaches to the molecule, only one face of chromosomal skeleton is available for the nucleophilic attack of benzylamine. As you see, the other face is blocked by the phenyl ring. Furthermore, hydrogen bond between nucleophilic benzylamine and the carbonyl group of cyclonamide group guiding its approach to the chromon. As a result, the reaction is diastereoselective. Domino reactions are another useful strategy to produce complex structures. In a domino process, several bond-forming reactions take place just in one step and without changing the reaction condition, in which the latter transformation takes place at functionality obtained in the former bond-forming reaction. You can check out my previous video about domino reactions to know more about this strategy. Now let's explore elegant synthesis routes which take advantage of combining multi-component and domino strategy to create complex structures, which are hard target in the classical approach. Indoloquinolizidine framework consists of 4 fused rings with indole core, which is of great interest due to its broad range of bioactivity. This motif forms the skeleton of some bioactive alkaloids. In the structure, controlling the relative stereochemistry of these two hydrogens is challenging. In 2011, Wu group represented a one-part double cascade 3-component reaction based on pictet Spengler cyclization and utilized an organocatalyst to control the stereochemistry of the reaction to produce indoloquinolizidine skeleton. First off, 1,4 addition of tryptamine to ethyl propylate gives the expected beta-N amino ester. Next, aldehyde and organocatalyst is added to the mixture. In this step, secondary amine as organocatalyst activates the alpha-beta unsaturated aldehyde by formation of a minium intermediate and set the stage for attacking of an amino ester formed in the previous step. Now look at the 3D model of transition state. Bulky substituents in organocatalyst blocks this phase of the alpha-beta unsaturated compound, so nucleophilic attack takes place from the opposite direction. This hysteric hindrance is the origin of an antioselective installation of the substituent in two positions of the final product. Domino continues with simultaneous intramolecular attack of an amine moiety to the aldehyde. In the presence of benzoic acid, hydroxy group leaves the molecule, and domino ends up with pictet Spengler cyclization.